Okay, in this part of the lecture, we're talking about nonlinear classifiers. And in the end of the last segment of this lecture, I talked about that now we have a way of transforming from an input space. And we can see how this is how the data is arranged. And if we have the right type of transformation, we can get into a feature space where there's a nice separation between the features. And one of the ways of doing it is something called a kernel. And we'll be getting into that in a little bit. From Sugiyama, just showing a couple other example figures. And so for a nonlinear classifier, we can see that we have something like this. This isn't a line, so this could be harder to doing things analytically, numerically. Here we see an example that we've done a transformation. So now with this hyperplane, if you will, now all of the circles are above that and all of the X's are below that or right on that. So that's why we're doing this using something called a kernel trick. Here is some of the supporting math that is behind the nonlinear classifiers. We look at the optimization problem. It changes now. Now we're trying to minimize this type of equation. It is quantified to something that we could compute, but let's continue to work on this a little bit and see if we can come up with a little bit more clarity in this. And so I'm not going to go through the math in general, but I'm going to try and give you just a high level view of this to give you a perspective on this strategy. So the decision boundaries become this. And so we have this equation. And then we can be asking the question, is there a need to know the mapping of phi? And the answer is no. So this can be helpful. So the support vector machine, in this support vector machine, this is done through the use of the kernel function denoted by K. There is no explicit need to know what phi is. And so this is an example of a kernel function that we're starting to introduce with that equation. So let's now talk about constructing kernels. And does any kernel work? And the answer is no. Only a valid kernel function works. Identification of phi is not needed if it can be shown whether the function is a kernel or not without the need of mapping. The function satisfying Mercer's theorem can work as the kernel function. Mercer's theorem, which provides a test whether a function k constitute a valid kernel without having to construct the function phi. So what I'm just trying to point out is the existence of a kernel. This is the way that we can do this type of a conversion. And we saw this with our basic text. Here we're seeing that the terminology phi of X that we have here from Sugiyama, it has a slightly different way of using some of the syntax for the equations, but it's still the general idea. So kernels can be a useful thing. And so common kernel functions that are used, we have the polynomial kernel of degree D. And so this is the equation of what that would look like. We can have the Gaussian ratio basis function kernel, the RFBF. So here is another type of a kernel function that we can be using to help us to create that separation. What are some of the common decomposing multi-class classification problems that come up when we're trying to decompose them into binary classification task? And so we'll talk about two. One is something called the one against all, the OAA. Given M classes, M linear decision surfaces are made. Each decision surface is trained to separate one class from the rest. To classify an unknown point, a voting scheme is used based on which of the M decision surfaces return the largest value for the unknown point, the decision service that results returns the largest value as a class of that point. So one characteristic at a time, we figure out what is best, and then we try to aggregate them together at the end. Another strategy is a 1 against 1. So here we do pairwise classification. We train a classifier for each pair of classes. And we end up getting a vector trying to look at the wins that take place. And the final decision is made by looking at which one has the most frequent class. And so that ultimately is what we're trying to do with that. So support vector machines conceptually can be a little bit more difficult to get your arms around. And we've talked about a couple different ways of how that could be helpful, where we're trying to do this translation, if you will, from one type of an input space to a feature space. Then we spoke about some of the possible more complex ways of analyzing that data, and also what are some possible kernel functions that we can use for doing that separation. So make sure that you do take some time to look over the material in the textbook to complement what we discussed here in this lecture. Thank you very much.